translations. I know. That's so funny.
Okay. Were you here last Friday?
It's like the gravity will certify.
I know.
It's like,
If we did that tomorrow, let's see if we also make the same thing.
That's not.
They're all of a sudden, number 12, you know, that they- there's only- Like, days right now.
Hey guys, page 6 in your packet. Yeah. Let's review applying these properties. So we'll look at page 6, the last two problems there, 59 and 60. Okay, so we talked about how we can apply expansion properties. We can apply expansion. We can apply expansion properties before we apply our derivative rule, if there's a property for us to apply. So if we look at 59 here, anytime I see a natural log, we always want to explore the possibility of maybe splitting up into individual or smaller problems before we jump into the derivative, because we prefer to have a smaller u value if we can help it. All right, so 59, which property can we apply to allow for that to be a easier problem to work with? Okay, quotient property, right? If I have natural log of a over b, I can expand that into natural log of a minus natural log of b, right? So we can go ahead and start separating the two terms using subtraction between the two terms. Okay, so my numerator I can think of as the a value, my denominator as the b. So natural log of a minus natural log of b. What else can we do? The radical we can rewrite raised to the 1/2. And then continue expanding by, that power property. Okay, so when you bring that 1/2 down, this is not derivative rule. We don't bring the 1/2 down and subtract 1 from the exponent, right? That's not, there's no calculus yet. But we're getting all the way down to this point so that our derivative step will feel a lot easier. So now we can apply our derivative rule, right? The derivative of natural log is u prime over u. So the 1/2 stays. And what's our u prime going to be? 2x, yep, this derivative of my parentheses divided by 4 plus x squared. And then the second term here, natural log of x becomes 1 over x, yeah. Do a little bit of cleanup. The 1/2 and the 2 can reduce. And we have we don't have to find common denominators. Here's our y prime. Okay, take a look at number 60. Can we expand this problem? Does it match any of the properties that is available to us? it feels like we could, right? It feels like we could distribute the natural log through, but we could only do that if natural log was something that's outside the parentheses, right? But that x plus root 4 plus x squared, it's inside the natural log function. So unless it's like natural log of x, unless this is the independent expression, let's say if it was like natural log of x, then I can distribute that through. But this is inside. I can't distribute something that's inside an expression. So we're kind of stuck with this being our u value. So we have to jump directly into our derivative because we can't really do anything with this parentheses here. So to get to u prime, I'm going to first rewrite my expression. What is going to have to be involved here if I want to find the derivative of this full expression here? Chain, right? There's power rule here, but there's a bit of a chain here. So outside derivative times inside derivative, and all that is going to take the space of that u prime. And then we can do divided by u, which is this full expression. Okay, so 1 plus outside derivative, bring down the 1/2, keep the parentheses, subtract 1 from the exponent, times the inside derivative. Inside derivative is 2x. So all this is going to represent my u prime divided by my original u value. Okay, we do a little bit of cleanup here. The 2's can reduce. We can put this negative 1/2 in its own fraction, but we can't really push this negative 1/2 down to this denominator because that plus is kind of forcing it to just stay within this region. So this is as far as we need to go. I mean, we could find common denominators and clean that up, but that's fine.
Why did we subtract 1 from the exponent this time?
Because this is a pure power rule here. Right? If it was within a natural log expression, then we could bring that down and do the final review. This is a standalone parentheses of 1/2, which we can do using power rule. Let's turn to page 7, the next page, and I want us to do number 74 and 76. Okay, a little bit of a review with some previous topics. Everybody okay with 60? Okay, so let's look at 74. Okay, so we want to find the derivative, dy dx. We are going to eventually find the derivative, but is there anything that we can do before we jump into our derivative process for 74? Expand, right? So anytime I see a natural log expression, this xy is a part of that natural log expression, right? We can split that up so that our u value is not as messy as that. So we can definitely take some expansion properties before we consider our derivative rule. Okay, so we definitely have to involve natural logs derivative, but something else we have to keep in mind. What's different about this problem or the way that's set up? Okay, which variable requires some special attention here? Y. See that this is not a y equals, right? This is not a function where the y is completely separate from the rest of the problem. We have to apply implicit. So we got to keep track of our dy dx. It's going to pop up within our equation, and we're going to have to algebraically kind of move things around, get that dy dx by itself. Okay. So let's jump into our derivative rule here. Natural log of x becomes 1 over x, u prime over u. Natural log of y becomes 1 over y, but because you're good, because we're including y's derivative, we need to attach that dy dx. 5x becomes 5, right? We don't do anything special with the x variables, just the y variables. Equals, good, 30 also gets impacted. We don't leave that 30 alone, we turn that 30 into a 0. Okay, the calculus is done. Now we just want to move things around and get that dy dx by itself. Okay, multiply both sides by y, by the reciprocal to get my derivative variable by itself. We just distribute that y through and that's fine. Okay, 76. Is there anything that we can do prior to our derivative process? Expand, yeah, natural log of x squared y can be taken care of. That our derivative is a little bit easier. Natural log of AB can be expanded into natural log of A plus natural log of B. I could move that 2 down, just to fully expand, but not too bad even with it there. Okay, so again, y's are mixed into the equation. We definitely have to involve implicit, but there's something else that we have to be aware of. What other derivative process are we going to have to need to use? Say it again. Has to do with this 4xy here. Product rule. Good, right? X and y are multiplied. I can't merge that into one variable. It's stuck as 2 separate variables. Anytime a multiplication of 2 separate expressions are involved, I have to apply product rule. So this is my f and this is my g. So all this is for this 4xy. Okay, 4x becomes 4. G function, no changes. Back to f. Okay, g prime, what's y's derivative? Right, 1 dy dx, right? Okay, so I'm just going to put dy dx here. That 1 I can just leave out. Okay, so we're done with the difficult part. Everything is individual. We can just take care of them separately. So 2 natural log of x becomes 2 times 1 over x. Natural log of y becomes u prime over u, but we need to attach that dy dx. And then the 7 goes to a what? 0. Okay, we have 4 terms that we just want to kind of move around, try to get my dy dx's together. So I have 2 dy dx terms. I'll leave these 2 on the left side and I'll go ahead and move the others to the right so I can factor the variable that I want to eventually get by itself. Okay, factor out the dy dx. I can put the expression in parentheses and then divide over. Okay, page 10, I want to do a little bit of review from what we did yesterday. We talked about inverse or derivative of an inverse at a point. So go to page 10 and let's do number 12 at the very bottom there. Page 10, bottom of page 10. Okay, so page 10, number 12 here. So we talked about yesterday how a function and its inverse are going to have order pair relationship, but then a function and its inverse at their different points are also going to have the shared slope numeric relationship. Okay, so let's review that a little bit. I like to create a little table here, chart, to kind of help map my progress. Okay, I know that my derivative, I'm looking for the derivative of an inverse at a point. I'm looking, my x value for my inverse is 11. So I'm trying to find the derivative of an inverse at 11. Okay. What I'm going to do is I'm going to make my way around this chart. I'm going to put my information, my order pair information between my inverse function and my function up here, and then my slope relationship between my derivative and the derivative of inverse down here. Okay. So I know that my inverse function has an x value of 11, which means that if 11 is the x value of my inverse, then 11 must be the what? The y value of my original function. So I'm just trying to fill out as much as I can just based off of that information that I know about 11. So now I'm just going to fill in the gaps because I want to make my conclusion about the derivative of the inverse function, but all I have to work with is the function. So we have to get all the information that we can from the function side, and then finally we can make our conclusion purely based off of what we find on the function side. Okay, so the next step is we're going to be looking for the x value that will fulfill this order pair. Okay, we know what the y value is. We have the function, so we kind of work backwards to figure out what the x value is. So I'm going to insert this 11 into the y value of my function. Okay, let's go ahead and move that 11 over just so it makes it a little bit easier to see what we can do here. Subtract 11 from both sides. Okay. Now you're going to see this in, if you saw it in your homework, there are some problems where you're not going to be able to factor, and you're just going to have to rely on guess and check to figure out what that x value is. But the good thing is that the number should be easy to find. It should be a number that is between -3 and 3. So just have to go through a series of small numbers until you can get something that will work. So usually I start with 0, then I try 1, then I try -1, and just kind of keep going with that. So any guesses as to what an x value could be that could make this equation work? 2. Okay, let's try that. So if I plug 2 in for x, 2 cubed is 8. 8 times 2 is 16. 3 times 2 is 6. 16 minus 6 is 10. 10 minus 10 is 0. So we have our x value. So we can kind of start filling out our information here. Our function in inverse will always have flip-flop order pairs. So I know f of 2 is 11, which means that f inverse of 11 must be equal to 2. So now we're going to jump down to the derivative side of things. If I can find the slope of the graph at 2, then the number that I find, this slope is going to be directly related to the slope that I'm looking for. Okay, but this we can do on our own. We could do based off of f of x. If I want to find f prime of 2, I can first find what? First find f prime of x. Yep. So let's find f prime of x. Derivative, this is easy here. What's 2x cubed minus 3x plus 1's derivative? 6x squared minus 3. Okay. I can figure out the slope on my f graph side of things by plugging 2 into the derivative. Six times 4 is 24. 24 minus 3 is 21. So the slope on my f graph is 21. There's a numeric connection here between this number and the number that we're looking for. The slope is going to be what? Yeah, and it's always just going to be the reciprocal. You're never going to change the sign. Keep the sign, just flip the number. So we're trying to find information on the inverse side of things, but all of our work is on the function side of things because that's what's given to us. So your order pairs will be flip-flopped between a function and its inverse in terms of corresponding points. And then at their specific points, these are different points on the graph, their slopes will be reciprocals of each other as well. Will be reciprocals of each other. All right, let's look at notes that I have for today. Turning to page 13. Okay, let me talk about some relationship here between natural log and exponential function e to the x. All of our we've done some work with natural log, and now we're going to talk about natural log's inverse function, which is exponential function e to the x. So I'm just going to put some notes here. Natural log of x is the same thing as log base e of x. ln is just a shorthand way of saying log base e. So you kind of see that this is base e, and kind of see that e to the x, there's going to be some relationship there. Visually, you can also tell that natural log and e to the x are inverses of each other because natural log of x looks like this. And e to the x is an exponential function, looks like this. And the two graphs, we can imagine folding across the diagonal line and the two graphs overlapping each other. So a couple of properties to kind of demonstrate the fact that if I pair a function and its inverse together, they're going to have a way of kind of undoing, canceling each other out. And the nice thing about that is it allows us to solve equations because we're able to either get rid of an exponent or get rid of a natural log. So here are the two properties that we're really going to be kind of using. We kind of have seen some of it. If I have natural log of e to the x, right, that x can come down, and I'm just basically left with just x, because natural log of e becomes 1. It's basically saying log base e of e to the x is just equal to x, right? If I insert an exponential function into a log function, they're going to cancel each other out, leaving me with just x. Okay. The other property that we're going to explore is this. If I have e raised to the natural log of x, that's also going to become x. So if I insert the natural log into an exponential function, they're also going to cancel each other out. The reason why is because natural log is log base e raised to log base e, they're just going to cancel each other out. So if I plug one into the other or the other into the first one, they're going to cancel each other out. Okay. So we're going to explore those two properties with example 1 and 2. Right, so 7 is equal to e to the x plus 1. There's no calculus here. We're just going to try to solve for x. We talked about how if we take the natural log of both sides, we can bring that exponent down, and we have a much easier time to work with that x. But also, e and natural log have a nice inverse relationship, so we know that will also take care of each other. But so twofold, we know natural log and e are going to cancel each other out, but we also know that natural log will allow exponents to come down, allowing us to move that variable that we're trying to solve for. Right, I'm taking the natural log of both sides to force that property, that log property, for us to use. So what can we do next? What property can we use? Power property. What can we do? Right side. X plus 1 can come down, right? Without changing overall value. That's just power property. Right, do you guys remember what's natural log of e is equal to? 1, good. So 1, you could just let that disappear, because 1 times anything is just whatever that thing is. Drop the parentheses, natural log of that 7 equals x plus 1. Subtract 1 from both sides, and all of a sudden I'm able to solve for x. Okay, number 2, natural log of 2x minus 3 is equal to 5. Okay, so I want to solve for x, but you see how x is stuck inside the natural log expression? So what I'm going to do is I'm going to find a way to get that natural log to disappear. The way we can do that is we can basically raise both sides with e as the base. And the advantage here is we know e to the natural log is just going to cancel each other out, right? But we're not just doing this to the one side, we're doing this to the other side to maintain balance. But if I can get e a natural log to go away, then that's going to free my expression to allow me to move things around and eventually solve for x. So that 2x minus 3 is going to drop down. Now I'm able to freely move that x around, where before I couldn't really move it because it's inside the natural log. But I've released that expression out from under the natural log, and I can solve for x now. Add 3 divided by 2. Okay, so now let's talk about the derivative rules that we can use for exponential function e to the x. So here is the derivative rule here. The derivative rule is e to the u is just e to the u times u prime. So that's nice. The derivative of the exponential function e is basically itself times the exponent's derivative. There's a little bit of chain rule. If that u is anything more than x, we got to take care of that, its own derivative. So e to the u times u prime. Okay, let's do a example before we jump into example 3 here. So let's try this one here. If I have y is equal to e to the 5x squared minus 9x, let's see if we can practice doing the derivative here. So we have our expression here. Our u value is the entire exponent. Okay, let's follow the rule here. The derivative of e to the u is just what? Yep, the exact expression. You're just going to copy the function. The derivative is just the function itself. But we got to worry about the u because that u is pretty extended here. So we got to do u prime as well. Okay, what's u prime? 10x minus 9. There it is. That's our derivative. All right, so let's look at some problems where we're going to have to kind of merge a couple of different rules. Let's try example 3. Find y prime for y is equal to natural log of 2x minus e to the negative 2x. First step is, this is a natural log expression. Maybe we can try to expand it, but this one we can't. Okay, there's that minus sign in between. This is not product property or quotient property. We're stuck with this parentheses being our u value. So we're going to jump directly into our derivative, u prime over u. So u prime is just the derivative of my full parentheses. So we'll take care of that. All right, so I'm going to look inside the parentheses and take each derivative and put it in my numerator. 2x becomes 2 minus, okay, now I'm dealing with the e to the negative 2x. I have a special rule for that. That's e to the u. So what's e to the negative 2x derivative? Yeah. So all that is sitting in place of that u prime, that this represents the derivative of my u value, which is inside my natural log expression. But then I still got to finish this off and divide by what? Divide by u, right? And u is my full parentheses. Okay, so we don't have to do too much cleanup with this derivative. I'm just going to put these together a little bit. Okay, we can't cancel anything out, right? That plus sign is preventing us from doing anything, so we're kind of stuck with that form. Okay, all right, let's look at number 5. I'll put this on the separate sheet so I can see all the steps a little bit more clearly. We're going to skip number 4 here, so we're going to let's look at number 5 here. Number 5 says find the equation of the tangent line to the graph. So we're going to find the derivative, find the slope, and then point slope form. Okay, so we definitely have to involve the rule for e to the u and natural log of u. What else do we need to make sure we apply if we do want to find the derivative? Yeah, these are two separate terms separated by multiplication. I got to go through the product rule if I do want to find this full derivative. Okay, so I'm going to spell out product rule here. All right, so let's apply each part of these terms here. E to the negative x becomes, what's the derivative? Times -1, right? My u is the negative x. So e to the negative x times -1. So that represents the derivative of my e to the negative x times the g function. No changes there, natural log of x. Plus, back to f. And g prime, my natural log of x. What's my natural log of x derivative? 1 over x. I'll do some cleanup here, but not too much, because I'm just going to plug in that 1 there. All right, so whatever I do with my derivative, I just care about my slope. So I'm going to start inserting 1 into the derivative, because if I can replace all these with 1, I should be able to get it down to a number, and that number is going to be the slope that I'm looking for. Okay, looks like a mess, but there's something nice about this one here. What's natural log of 1? 0, which means I can remove this whole thing, right? Anything times 0 is going to be 0. So I'm just left with e to the -1, which is the same thing as what? E to the -1 is the same thing as, if I were to move that with a positive exponent, what would that look like? 1 over e. There's my slope. There's my order pair. Then I can build my tangent line equation. All right, let's try number 6. Okay, so number 6, the instructions are to find dy dx, to find the derivative. So let's name a couple of things here. What do we have to be aware of that we have to make sure that we include as part of the process if we want to find the derivative? Implicit, yeah, you see y's all over the place. You know you got to keep track of your dy dx's. Okay, what else? Yeah, that x and e to the y, I got to go through product rule there. Okay. Okay, so f prime becomes just 1. G function, no changes. Back to f. G prime, what's e to the y's derivative? E to the y times dy dx, yeah. right, so all that is to take care of that x times e to the y. Keep going. These are just individual terms here. Negative 10x becomes minus 10. 3y becomes. All right, so we have 4 individual terms. With these 4 terms, we're just going to try to get the dy dx terms together so that we can group them together, factor out dy dx. Okay, so let me just clean this up a little bit before I start moving things around. So I see the 2 terms that are clearly including and has the dy dx. So I'll group those 2 on the left side. That way I can factor my dy dx out. So once I have that factor out, I can isolate my dy dx variable, derivative variable, by dividing the parentheses over. Okay, let's do one last problem here, number 7. Yeah, our last one. So number 7 is kind of like a merging of 5 and 6. Okay, we're going to take this problem, but we just have to go one step further and find the slope so that we can get into point slope form and find the equation of tangent line. So take a look at number 7. I want to find the equation of tangent line. What process is involved, like how we saw before? Yeah, implicit and product rule. But how many times for product rule though? Twice. Yeah, that x and e to the y, I gotta go through product rule there. E and y e to the x, that's another set of product rule there. Okay, so let's build out our derivative here. F prime g plus fg prime, I gotta do that twice. X becomes 1, we keep the e to the y, we keep the x, e to the y becomes e to the y times dy dx. Then we'll repeat the process for the f prime g. Y becomes dy dx. E to the x stays. We keep the f. E to the x becomes just e to the x, right? The derivative of e to the x is just e to the x times 1. No changes there, and the 1 goes to 0. Let's do some cleanup here. Okay, so I have 4 terms. I can clearly isolate my dy dx together. Factor out my dy dx. Divide my parentheses over. Okay, so now we can do what to find the slope. Plug in what? Order pair, right? Because it looks like it needs both the x and the y value. So Oh, sorry, this is, oh, sorry, 0, 1, 0, 1. Yeah, you're right. So if I plug in 0, 1, I end up with a slope of negative e minus 1. My order pair is 0, 1, and then my point slope form. There. All right, go up and get your phones. I will check 5.4 homework tomorrow.